Okay. So let's get started. Um, uh, I guess people can hear me, right? Okay. Um, yeah, today we will talk about resource efficient fine-tuning. This is a topic which actually has a practical importance in the sense that if you want to train like models in academic environment where resources are limited. I mean, this kind of technique all matters. So we actually go through quickly the ones which are more important. Some are probably more detailed, some are less detailed. But essentially, if you want to train that, then these are the methods which you can use, especially for the academic resources. Okay, so let's talk about the what we want to talk about today. The key idea for this kind of a resource efficient fine-tuning is GPU memory, basically. Um, Usually, you have to fit your model into GPU in order to compute. But the GPU has the limited memory. Nowadays, GPU is reasonably large, like 40 gig and 80 gig, even larger. In the years a little bit earlier, it was more of an issue when you have a smaller GPU, like 24 gigabytes. But even now, this still matters because some larger models indeed will consume a lot of GPUs. So the idea about this will be actually how do you save GPU memory. So essentially, this is most we will talk about the techniques that make it happen. Um, we will first talk a little bit about how these models training work with CPU GPU architecture like parallelism and so on. Also arithmetic precision. So this is also very typical for this kind of training. Part of that is speed. Part of that is memory. Then we'll talk a few techniques. The main techniques which matters is one is this zero offload, which essentially says you want to put some optimization state part in CPU, part in GPU, assuming you have a much larger CPU memory. Then you also have this gradient checkpointing, which is saving these states where you basically need to store in the forward session in terms of computer backward. When you have a backward, you need to save all the activations in the forward in order to compute the backward pass. This one try to reduce that consumption. Flash attention we'll talk a little bit about. This one is useful for longer sequence. The way it's handling attention. It's a simple idea, but generally it needs that. LoRa is another technique. It's adapter technique. There are various adapters being studied in the past few years, but the one actually survives. The most nowadays used is this low rank adaptation, and along with the low rank, there is Q LoRa, which is a combination of the two idea. One of idea is the low rank, the other one is quantization. So basically, yeah. So basically, this is a kind of structure we will go through. It's quite a bit of ideas, but in reality, a lot of these ideas not that complicated. So once we explain that, probably you can summarize in one sentence or two sentences. So therefore, even though there are a lot of ideas, at a high level, when you understand that, it's can be pretty simple. Yeah. So that's why we will cover a lot. Okay. So these are the topics for today, and these are the most important, I would say, the topics when you want to train these large models when you have a limited memory. So let's look about GPU memory for fine tuning. Certainly, we know that large model fine tuning will require significant GPU memories. Later, we'll do a calculation that you will see how much it needs. It's actually quite a bit. Um, and if you think about GPU memory, right, what is actually is needed, right? So where it's needed for? Certainly the parameters, the model size. Model size definitely matters, right? So model size is a key factor where you need. There is also model architecture. That also matters. Part of the reason is when you look at the model architecture, when you look at the training, when you do the training, it's not only model parameter that matters. You need to compute the gradients. You need to store optimization. And before you are computing gradients, you also need to save the activation in your forward pass in order to do your backward pass. So some information need to be saved in GPU memory. And that information will be affected by model architecture. So therefore, model architecture depends on how much you will save in the forward. Like MOE, you may save a fewer forward. So this saves your computation. Optimization states, particularly we're using Atom. Atom, besides your gradient, you have V. V is the velocity, or V is momentum, or you also have you have a momentum. Also, you have the V actually is the square of your gradient average. So basically, you have two more, and that actually matters. So that actually consume quite a bit more memory, as we will see, than the model parameter itself. So then you have a data and a batch size, right? Data certainly you need to, and your more batch, data will go to GPU. So that's one consumption. The other one affecting batch size is when you do the forward, you need to save activations, and that one will grow proportionally when you have a batch size growth. So essentially, a large batch will cause much more GPU memory because of that. So all these issues point out that eventually we want to reduce the memory usage. And then we will come to different ways, all these issues, so where you actually affect, and then we have different solutions. So basically, model, what you can do is model parallelism, and also mixed precision and quantization. So this we will first talk about. Then you will also have the trainable parameters that can be reduced. So this is a LoRa. This is an adapter idea, which again, there are many adapters has been proposed, but the LoRa is the one survives most. So we will talk about that in particular, the adapter. Then you have optimization, right? Essentially the optimization states in the atom, which is V and W M, right? So basically, yeah. And then you have the data, and then either reduce the batch size, or you reduce so-called this gradient checkpointing, which reduce the activation stored in GPU. So basically, all these approaches is aligned with whatever you want to do. And then we will go through these techniques, try to kind of one by one, the most important ones. Before we do that, so we will first look at the memory architecture for model training, right? Essentially, one thing what we do is usually data stored on disk, right? Then you load the data to the CPU memory. So CPU has all the data. Eventually, data also need to go to GPU in order to do the computation. So after CPU, you do the processing, and then you goes to the GPU. And once you goes to the GPU, GPU model will be saved in the GPU, right? So, and then you also need to do gradients, calculation, and also model activation. Those will be saved in the GPU, as well as optimization state. Optimization state, actually, you can move out to the CPU, which is when we have this so-called offload, which we will talk about. This one saves memory in terms of moving the optimization states from the GPU to CPU. So basically, usually you have a multi-GPU setup in the larger trainings, and the model can split into the mini batch. This is called data parallelism. They will go to different GPUs. Also, model itself could be partitioned among the GPUs if you have a larger model. But in the academic setting, typically what we do is each GPU contain a full set of the model parameters. So models are not parallel across the GPU, but actually they are shared. They will sync among the GPUs, but each GPU copy the full set of parameters. That's more typical in the academic setting. In the industrial setting, very large models, then you have the distributed model parameter among all the GPU. So we could quickly mention how that is done. Then this is not our focus. Our focus on the later techniques, which more matter in the sense of model will every GPU has one single copy of model. So multi-GPU parallel strategy, data parallelism, right? We mentioned that basically, all the model, this is typically academic setting, all the models are on multiple GPUs. And each GPU process different part of the training data. You have a mini batch, say if you have mini batch 256, right? You have 8 GPUs, then you divide by 8. It's a 32 mini batch among each GPU. So each GPU corresponding to 1/8 of your total mini batch, and therefore you could process parallel this mini batch by using all the GPUs. Then you synchronize gradients, right? You compute the gradient for each GPU, you synchronize that to keep a model parameter consistent, and so on. So basically, essentially you have different data, you have a model, gradients, and a synchronized gradient, then you calculate the updates on each GPU. So this is a standard way in the data parallelism, while model is not parallelism. Okay, there's no model parallelism. A model is basically copied directly on each GPU, and you synchronize among these GPUs. This is a much more typical setting in the academic environment. Usually, if you want to train a model, this is the way it's done. So we are focusing on this setting, and later a lot of techniques along with this setting. But before we doing this setting, we will talk a little bit also quickly talk about model parallelism. This is data parallelism, right? So model is occupied for each particular GPU. Model parallelism, there are two main approaches. This one is a more dominant approach. This is it's a Amedia's work. This actually known. I would say, they are not inventing this. It's just in this particular context. If you cite who is doing that, this is a paper. They have this called Mactron. It's an open source project, and then they use quite a bit of this. Essentially, you split particular matrix weights across multiple GPUs based on the observation that matrix multiplication can be parallelized, right? So if you think of matrix multiplication, the rows are independent. So if your row times column, and the first weights are independent. Therefore, you can actually parallelize that. And each will essentially hold a part of your matrix weights. And when you do matrix multiplication, this is the most time-consuming operations in all the GPU. Right? GPU essentially is a way to parallelize your matrix multiplication. And then you can across the GPU, because you divide this data across the GPU, you can also divide your weight matrix across GPUs. So essentially, each GPU contains a small set of weight matrix, and then you do this local matrix multiplication, you get it together. So this is, I believe, by far is a more predominant one in the sense of how the parallel is done, and this one is again, this is known well before the paper, but this paper essentially try to implement better in the GPU setting. Yeah, so basically, yeah, this is one approach. Another approach, which I believe is less popular but still used, is more of a pipeline approach. So basically, the idea is you can also separate your layers instead of matrix, right? You can separate your layers. If you are thinking about transformer has multiple layers, then each layer can be put in one GPU, and then you do a pipeline. So basically, let's say you have 8 layers, 8 GPUs, 8 transformer layers, right? Each transformer layer can be put in one GPU, right? So basically, for the pass, each GPU will be compute a portion of the model sequentially, and then you go through backward passes in reverse order. Basically, you try to feed the GPUs such that each GPU does one of the job only, right? Then you have a pipeline. So when you have a pipeline, you have to make sure they are synchronized and so on. So there's a delay. But nevertheless, assuming delay is low, and then essentially you are doing, this is one example. These two layers correspond to this GPU, these two layers correspond to another GPU, and so on. So this is another way to do that, which the disadvantage of this, of course, is that it will actually have a delay, right? So you are not doing that in parallel GPUs. Then you have to you do that smartly. Basically, you have a pipeline, right? So this is another approach. Both approach can be used to parallel your GPU, so that the efficiency can be done. These are the two ways to do model parallelism. Usually, we don't do that in the academic setting. So therefore, what we focus on again is just distributing data across GPUs. You can think about that model is in each GPU separately. I mean, this one, like model parallelism, is more advanced. It's mostly done in the industry. So let's look at what matters, right? Let's think about focusing on the issue about, say, data distributed across different GPUs and the GPU's store model. Now, what you can say in terms of the GPU memory? One thing immediate, which is pretty standard way to do that, is a so-called mixed precision calculation or training. This one is for the training. Essentially, you are using, instead of usually in the standard CPU computation, a floating point is 32 bits. It's basically it's 4 bytes, right? Double precision is 64. It's 8 bytes. But we usually work with a single precision, which is 32 bits, 4 bytes. But in the GPU computation, in machine learning, usually they do not even do the full precision, the single precision. They are doing half precision. Half precision is a floating point 16. It's a 16 bits, 2 bytes instead of 32 bits, right? So basically, we will have a mixture of that because in the learning, it's high precision. It's not like scientific computing. High precision is not as important. We need a relatively loose precision, but we need a large scale. So that's why it makes this one. Essentially, you use training. You use high precision, which is 16. And then you also mixed with 32 precision. So we'll talk about where you should use high precision, where you should use the full precision. The benefits of this is reduce the memory. So basically, when you save a model used to be 4 bytes, now becomes 2 bytes, therefore reduce memory up to 50%, right? For example, if you are 8-bit model, 2 bytes makes 16 bits GPU memory rather than 32, right? So this is what you want here. And this is pretty standard. People notice that one doesn't affect as much. So it also increase training speed on compatible hardware. The modern GPU, they all support native half precision arithmetics. Therefore, it can compute faster because you have a less big to work with. So therefore, this one is another advantage. You could actually do more computation, more speed up. So here is a standard full precision, which is a single precision of floating point in the IEEE standard, right? So this one, basically you have exponents. Exponents means you actually is power, right? So then you also have a very long bits about where this precision comes in. In the 16 precision, this one much more reduced. So this is a total 16 bits. You have 5 bits exponents and 10 bits of your fraction. So this is one way to work with 16 bits. Then later on, there's this is the IEEE standard. Then they are discovered at this Google. Google discovered you use so-called BF16. It's a different ways to represent 16 bits, right? Essentially, you have more range than the precision. In machine learning, observation is that precision isn't, for example, a few, in the second, let's say second order precision, let's say 0.001, 1.10 versus 1.11. It doesn't make too much difference. You just have a small decimal, so you need to represent that fewer bits to do that representation. But the range sometimes can have outliers and so on. So you use a larger exponents. So if you look at these larger exponents, it's compared with the FP32. Right. The only thing is each one is mapped with a smaller range, with a smaller precision, which this one you can think about is adding a noise. So essentially, noise is always in the data. So at this precision, it's so this is regarded a little bit more advantage than the original FP16. Usually, both are supported in the modern GPU. And a lot of people using this one. Sometimes you can observe a difference, sometimes you may not observe a difference, but essentially for half precision, there are 2 options. One is FP16, one is BF16. BF16 is it's like a brain floating point. It's a Google Brain's basically solution for this one. Yeah. So these are the standard way. So usually in the training mixed precision, you will use one of these 2. Yeah, many probably choosing this as a default. Yeah. Okay, so this one is for the precision. There is even more aggressive ones for the quantization. Quantization is instead of using 16 usually is reasonably standard. You can use both for training and inference. But for the inference, people notice you can even use fewer. So not only 16 bits, you can use 8 bits or even 4 bits. And this one saves your both memory and also increase your speed because a lot of modern hardware are starting to support this int 8 or int 4, right? So mixed precision comma in the both inference and for the training. Lower precision, like quantization. Quantization means you are not using even 16 bits, you are using 8 bits or 4 bits. These are common in the deployment inference. Later, we will see that in the Q-LoRa, it combines this one in the training because part of the model is freezed for inference only. So this is why it could do that. But people observe that if you reduce from FP60 to int 8 or even int 4, the accuracy reduction or the performance doesn't drop as much. So therefore, it's reasonable to do this. So memory reduction for model weight, right? If you think about the FP16, it's a 2 bytes. Int 8, essentially, it's a 1 byte. Int 4 is a half byte, right? So basically, you are saving 2 times and 4 times. So this is the advantage. And speed-wise, it could depend on your hardware. So basically, this is a kind of advantage. Of course, there is a quality loss, but people observe that, say, if you do, for example, if you do a large model with int 4, right, versus a smaller model with, say, FP16, right? Usually, the larger model with int 4 performs better than the smaller model with FP16. So essentially, the number of parameter matters more than the quantization loss, right? So the performance trade-off, a lot of people tend to use int 8 or int 4. Q-LoRa is it's using this in the training, but treating this quantization, we will later talk about that. Treating this as inference, the quantized part is only for inference. So this is why it works there. Anyway, so yeah, also there's other things. The memory with a KV cache, which we will not talk too much about. Yeah, here. But anyway, so one thing, precision versus speed. We just quickly go through that. Just have some ideas about what is happening here. So GPU speed, right? IP is the slowest, and the IP16 is faster. So because they are optimized for that, the modern GPUs. This one is even faster. So nowadays, GPUs also try to support int 8, int 4, so that you could even see a further improvement once you reduce. Yeah. Here, from int 8 to int 4, the memory probably is more than the speed. Yeah. For CPU, certainly IP32 is slower, but that is useful. Or slower than GPU. Sometimes people use that for inference, right? Int 8, if when you for the inference, right? So you either use int 8, int 4, if you do the CPU, right? Int 8 is reasonably supported in the CPU. Int 4 is less so, really depends. So I think maybe the future versions of CPU, they would be able to support better in the sense of that. But nevertheless, this just gives you a rough idea as current status about if you use different precisions, what is the trade-off for memory and the speed. And you have a certainly clear gain in memory, but speed gains is lesser so, depends on the situation. It's more variable, right? So yeah, so basically this is essentially what happens in the mixed precision. We are more focusing on the training, fine-tuning. Therefore, what we want to focus on is more on the AP16 and BF16 together with other techniques for the training objective. So let's look at memory efficient techniques, in particular for the training. We already know that we can use half precision, right? So that saves some memory. But then we are not talking about the calculation for gradients, calculation for optimization states. This is where the other things will come in. Zero offload is one technique which reduces optimization states. Turns out that actually occupies the majority portion of GPU, as we will see soon. Yeah. The other one is gradient checkpointing. This one is again is just when you compute the gradient, you want to either save all the activations or you want to save part of the activations. This one is reducing the memory, but with a catch of you are treating of memory into more computation. So then there's gradient accumulation is more about simulation. So this one we will quickly mention. This is something you can choose in your PyTorch program. Flash attention will quickly mention. I think the last two we will only quickly mention because the last two is just one sentence. You know what it is doing, and it's actually there's options when you look at the training which you can choose. LoRa is something we'll talk more about it. This is adapter technique, which using a smaller number of trainable parameters in your fine-tuning stage. So this is something we'll talk about, and also QLoRa, right? So that's related. Now let's look at again, we will start with the offload, which essentially will try to understand what happens with optimization memory when you look at, say, ADAM-W, right? ADAM-W is very common. So when you do both in the pre-training and the fine-tuning. So ADAM-W is something we will choose to discuss this. It's a mixed precision setup because usually we use a mixed precision, right? And then we can calculate what memory is needed to store parameters. We are not looking at activations at this point. But if you calculate just the number of parameters needed for your forward and backward, so you have a number of parameters, you have gradients. This one needs to be in the GPU because these are all computed. If you say optimization states, right, M and V, which is the parameters you need to save in your ADAM computation, then essentially these two have precision, the first two. Then you have 2 by 2, 2 times 2, 2 plus 2. Then you have 4 bytes of your optimization state. This has to be 4 bytes because if you're starting to reduce that, it will introduce problems into your optimization. So in all that, unfortunately, you have to use 4 bytes. So 4 bytes plus 4 bytes. So totally it becomes 12 bytes. So if you just look at the parameter, it's 2 bytes, right? Then if you look at all the trainings, it's 12 bytes. So if you are thinking about this is matters, then you see actually optimization matters quite a bit. Yeah, if you want to do this in more, everything is in the full precision. It could even calculate to the 16 bytes, right? But I mean, but essentially, 1B parameter, right? It becomes 12 to 16 bytes. Usually in the academic, people say doing 8 billion, right? That's very common now. Then you times 8, right? So totally it becomes kind of a little bit beyond. It's more like 100 bytes. Even you are not talking about anything else. You are just looking at this parameter storage. So this one can be very costly when you have suddenly starting to blow up, right? And then you cannot use the typical GPUs to train this. Then you either have to look at the model parallelism, which is more complicated, or you have to try to manipulate this, try to say, I need to reduce the parameter. one idea about reducing this parameter is if you look at how costly these guys are, M plus V is let's move this to the CPU memory, right? CPU memory you save actually 8 bits. Then suddenly you reduce significantly. So this is where it actually is talking about where it is. Yeah. The solution is either there's other factors which are reduce model parameters. LoRa also reduce this part because trainable parameter becomes smaller, but also you are specialize this or you have a zero offload. Zero offload move these guys to the CPU. So this is the basic idea about move M and V. If you do the calculation, then you see immediately why it matters, why it can save you a lot of memory, right? So their offload, the key idea is still keep the forward backward compute on GPU, but you move the offload memory heavy optimization states and updates to CPU. Certainly, the most computation is the matrix multiplication, right? So the GPU solve efficiently. For all the optimizer updates, they are actually not that costly. When you do that in the CPU or GPU, really doesn't make too much difference. So at least the computation wise. So here is the state. So GPU memory, you save all the model parameters. Here again, you need to save. This one we didn't show up in the previous calculation, but it's there. You have to do that in order to do the backpropagation. And then you compute the gradients and so on, right? So all this has to be in the GPU when you do the GPU calculations. Once you do that, you go through these gradients, right? You do the optimization updates. Here, optimization states and also you have master parameters. We can use 32 bits, and then you optimize GPU CPU updates. After you do the optimizer updates, you sync back to these model parameters, and then you do that, right? Typically in this setup, this computation isn't too bad. This computation isn't too bad. The main bottleneck is really this kind of a sync. This sync time depends on your memory, depends on everything, could be slow. So this causes some slowdown. This is why people try to later on talk about using LoRa and so on will be faster because they don't need this kind of a sync. Everything can be in the GPU. So if you can put everything in GPU, you can still be faster because of you don't need to have a GPU and a CPU memory bottleneck. So this one usually is more of a problem. Yeah, main game much lower GPU memory, right? So then you can really solve large models fit into your limited GPU memory. And this communication is certainly something which will be quietly expensive, depending on the situation. In many situations, this can be expensive. And typically, you have a GPU keeps this guy, right? CPU stores that, right? So basically, like this picture, and then, but this one is you can train some larger models. You cannot train if you're not using this technique. So this one essentially is a useful technique if you can tolerate this sync. So this is one technique we talk about, so we provide the notebook which contains all the technique we talked about here, including master. On master parameters, one question is about master parameter. Basically, you have IP632 about your model parameter. So model parameter, you are doing updates right here because it's a CPU. You can afford 32 bits. Everything is in the 32 bits here. It's just addition, and then you make it a high precision. You turn that into GPU. Okay. So master parameter means you have a higher precision parameter in your CPU. In addition to your optimization state. Yeah, everything is 32 bits. Okay. If that's clear, maybe I will just mention this guy. Maybe I will do a little bit of modification, make it clear in the slides. Yeah. But anyway, so this is what it is. Yeah. Now let's look at another one. Another one is dealing with this guy, right? So this guy needs memory, needs a GPU memory. Remember, this guy is for the backpropagation. So once you after backpropagation, this one completely removed, right? You don't need that. But essentially here, it actually matters, and this one also proportional to your batch size, also proportional to your contact size, right? Everything is because they matter. So essentially, this thing actually pretty quickly when you have a long context, a large batch size. So this one. So depends on and while model parameter doesn't. Model parameter really doesn't depend on the context size. Depend batch it could be a bit when you do the gradients because before the aggregation it does do that, but it be essentially here is the actually matters when you're starting to look into that. So during the training, intermediate activation must be stored for the backpropagation calculation. This is where actually calculation matters. In the standard setting, right? Every layer, every calculation, you need to save that. Basically, you need to save that, and you need to do that. Gradient checkpointing is basically say the following. Let's say I will remove this guy, for example. I just doing a few checkpoints. I'll skip some calculation. Then after I do the back prop, I will refill this guy. I can calculate this guy from this guy one forward step. So it's more expensive. You are doing more more computation. You have to do this twice. From here, you can estimate this guy. From here, you can estimate this guy. Instead of saving that, but essentially you are doing more computation. You are backward, which you already done in the forward. This one is the trading of your computation with memory. Because you are not, the point is, again, is you will not be able to train with longer context, higher batches. If you don't do that, you may not be able to, right? So this one is, although it's a trade-off becomes slower, it's still, you are able to do something which cannot be done before. So basically, this is basically the simple idea. So as long as you know this is fine. Essentially, you say, oh, I need to store these activations, but then this cause too much memory can cause some out of memory issues when you train with certain data. Then this one avoid that. So basically, if you see out of memory, you can think about different solutions like offload, or you can think about this is as one of solutions. Yeah. So basically, this is. Oh, it is. I think at this level, you right know that the details, how they implement that, it doesn't matter much. But essentially, this one is an option, which reduces the memory usage when you do the forward computation. So yeah, so basically, gradient checking point, the trade-off computational memory. You can train some which you couldn't before because it will cause out of memory in a GPU. And now, but then it's slower. So that's how many it is. Yeah. In level of the larger model, long context length or batch size, which originally you may not be able to do, right? Because as I said, memory activation memory, certainly you have to do all the batches, you have to do all the context lengths, right? So because transformer going through parallel goes to all the tokens, right? It's a longer context, the higher you need. So yeah, so basically, slightly more computation, but a significant memory reduction. So this is the key. Once you get out of memory, this is something you can think of. Yeah, that's all we want to say about it. So just have a high level understanding, and then you realize that what to use in the practice. Gradient accumulation is it doesn't actually, in some sense, it doesn't save the memory, or in some sense you can save depending on the view you are doing. This mainly to use a smaller batch size to mimic a larger batch size. If you say my algorithm has to work with, for example, batch height 32, right? And it doesn't work with a batch height of 8, then what do you do? Then you can say, I can still doing the batch size of 8 in my GPU because once you increase your batch size, you're increasing your activation, right? So then you gradually you greatly increase your memory usage. Therefore, you don't want to use a larger batch. Larger batch will cause out of memory, right? Even with gradient checkpointing. So, but then you say, I really do want to use a large memory. Then what happens? You just separate a smaller memory, which can be held into your GPU computation. But then you are just accumulate that instead of a sync across one mini batch. You are syncing across multiple mini batches. Basically, for example, you have a batch size of 8, gradient according to 4 steps. You are thinking after 4 steps, your gradient. You accumulate the gradients and think eventually after 4 steps, and then basically the effective batch size is 32. So essentially, it's a simulation. It's more about the simulation of effect of 8 batch size of 32 with a batch size of 8. So yeah, so this is sometimes helpful, but people may not necessarily use that if you are tolerate a smaller batch size. Usually, you can always use a smaller batch size without the gradient approximation, but tuning your learning rate, right? So, but essentially, if you know a solution which is good for the higher batch size, then you could use these. So this is an option, but it's not as dramatic as the other options. Yeah, but if yeah, so this is something. Another thing about is quickly mentioned, which is related to what we want to talk about. Again, we are just putting at a high level. These 3 we are putting at a high level. It's a flash attention. Flash is usually you need to use that, especially for the long context. It's actually a simple idea, very simple idea. They have different versions. So we are just talking about high-level ideas, but there are now I think even present 1, 2, 3, 4, right? So we just understand what we don't need to understand details about this what the difference of question 1, 2, 3, 4, but just overall high-level idea. High-level idea is for the attention computation in the traditional way to do that. It's a memory costly and it will cost trouble. And now you are doing that. Basically, you think about attention, right? It's actually matrix multiplication simultaneously across all the tokens. That is costly. The key idea is pretty simple. Instead of computing attention as a whole, you compute in blocks, which is actually not surprising. It's somewhat like the mini batch ideas in the data. Here, it's just using that for the context. You can think about context data, then you use a mini batch. So it's in this sense, it's related to this gradient accumulation, gradient idea, which you are doing that. So basically, to reduce memory at width, so we will see soon example. When you see that example, it's pretty simple. The traditional attention just using the full matrix. Now you are using this one is if you think about this matrix is context length dependent. Right, so the longer context length, the larger this matrix. It's L by L, if you remember this, right? In the attention calculation, it's L by L. L is the length of your context. And so, but if your length is too large, this is too large, the matrix, then essentially the idea is you split it down. So produce a exact solution, but which much memory behavior is just like this gradient accumulation. So lower memory usage and faster compute. I think I will just quickly mention these in the next you have a picture that is immediately say. Essentially, you just using a smaller blocks to compute this L by L, compute the block-wise instead as a whole. So that's all it is. Yeah, basically, the standard attention all simultaneously this L by L, right? So that's a huge matrix. Now let's say we'll make the blocks. This depends on how many blocks you want to, but essentially use one at a time. One at a time, then you just fill in one block at a time. Then you save your memory. So flash attention really try to reduce this memory usage. Instead of L by L, is depend on your block size. If your block size is B, it's a B by B. So each time, right? So this is your GPU memory, and then that solves the memory problem. And for the modern implementation, they all need to use flash attention, especially for long context size, right? So it reduces your effective computation, the complex size. So this is basically what it is. At this level, that's fine. But basically, there's a code available, which we are given in the notebook, which just if basically all you say standard attention, you replace by so-called flash attention. You just even you have a code, you just single line change of the code. A lot of modern models already support that, so you don't even need to change. You just say you use flash attention, but you need to install this flash attention package, and then it do that automatically. Basically, they all do that automatically for you. Yeah. So basically, they all support this. Yeah. Flash attention still compute the full attention, but it does that blah blah. This one, if you recall the similarity again, is much to do with gradient accumulation. Gradient accumulation is a larger batch using a smaller micro batch, right? Piece by piece. Here is attention matrix. You do a piece by piece. So this is a same idea. Most of that is like that. So basically, although there are a lot of papers, for details, they can write a few papers on that, right? But the high level idea is pretty straightforward. So that's why we can cover many different ideas, but you can see different ways where the computation comes in, where the memory comes in, and then the different solutions for that. Finally, we will talk spend more time on this topic as adapters, especially LoRa. So this is one of the techniques which probably a little bit more to do with machine learning. The other things is just quick ideas. Everybody it's more on the system side than on machine learning side. This one is more on the model side. So adapters and LoRa motivation, right? So basically, parameter efficient fine tuning essentially frees the most of the pre-trained weights and train a small set. This is called adapter. Adapter means if I have, for example, if I have 8B of my model, right? As we did the calculation, if we fit all into the memory, it's pretty costly, right? Each B is 12. Even just forget about the auto activation, all the thing you need to do the flash attention and so on. You still need quite a bit of memory. In terms of storing the model parameters and the optimization stage, which will be times 12, right? So 8B times 12 is 96, right? So basically, yeah, you at least that. You actually need more than that to do any calculations. This can be costly. So what we do is try to make trainable parameters to be much smaller. Instead of 8B, let's say if 1B, 8B plus 1B trainable parameters, then you can make much smaller. In the terms, instead of 8 times 12, you have a 1 times 12, right? 8 original parameter plus whatever trainable parameter, so it becomes 12, so it's a 20B, right? Then you are more manageable. So basically, this is the idea. You make trainable parameters small by freezing a lot of parameters. The key idea is full fine tune using all. It's expensive, as I mentioned. Even your 8B model, if you put everything in the GPU, it's like a 96B at least. And this is not only 96B, it's just all the parameter storage need 96B. Adapter only smaller set, right? Let's say if you have a 1B, and then it becomes 8B plus, it's a 20B, right? Significant reduction. LoRa is the one which is the most popular, and this is the most important and most widely used. So therefore, this is something we will discover. Although there are many other adapters that have been proposed, which we will not talk too much about. Okay, so we will focus on this one. So what is the LoRa? The key idea, right? Key idea is the following. So weight updates often have low intrinsic rank. So these are a nice observation. This is especially true for the attention blocks in the transformer. So therefore, a lot of LoRa starting, at least you need to do the attention. But also it can be applied for FFN. So you could also try to make this one for the FFN of your or MLP of your transformer. But basically, you starting freeze your original parameters, model parameters. Each one is one of the weight matrix. You have many weight matrix, right? But for example, your attention have multiple weight matrix. MLP has a different weight matrix. We all know that. And then this one is one of these matrices in the original model. You freeze that. You add a delta W, where delta W is actually your trainable parameter in your fine tuning, and then you essentially you say this one is a low rank, right? This trainable parameter. Now instead of you say this original trainable is a D out times D in. Now your is a D out times BR, right? R times D in. So therefore, if R is much smaller rank, say this D is like 1024, this R is 4, then you are saving a lot of memory. Basically, this one is a much smaller model. Yeah, significantly smaller. So this is actually key idea. Now I was just using trainable parameter become B and A, or you say low rank delta W. So and once I have this trainable parameter, everything depends on the trainable parameter, right? Besides one copy of this guy, trainable parameter determines activation, right? Determines your backward gradients, determine your optimization states. They all become smaller. So therefore, this trainable, as long as the trainable parameter is small, you are saving quite a bit of your memory. So basically, this is the key idea, making trainable parameter small. Here is an example. So basically, this is the input of your matrix. This is your pre-trained, fix your rate. And this guy is two trainable parameters, now become a low rank, right? And you just do an addition here. Again, you don't need to save anything about this. This one is just itself occupied. This one is associated with optimization state, with activation, with everything else, right? So basically, yeah. So this is something which you are actually covers that. Okay, so that's yeah. Let's do this. So Laura, basically, yeah. This is basically what it looks like. This computational graph, right? This is forward only. This one is forward backward. Right? So if you look at this decomposition, I think the key part is what benefits we get, right? The benefits what we get is the following: memory, will be state, right? Optimization will all be state. And the LoRa is speed is not necessarily guaranteed faster, but because you always need the forward is here. But actually it can be faster. Partly okay. If you say I can do the full parallel training, right? So the question is whether it's faster or not. Let's say limiting factor is not memory. It's not necessarily faster. But this one makes it which cannot be done in the GPU memory, now be all in the GPU memory. From that angle, it's faster. For example, if you say my model originally, if I do not use LoRa, I want to train this model, I have used CPU offload, right? CPU offload, which can be much slower because of this communication. Here, everything can be in the GPU memory. Therefore, the speed compared with the CPU upload, it can still be much faster. So from that angle, it's faster. But if you're just counting, if you have an unlimited GPU memory, what happens, right? It's not necessarily fast, right? So basically, depends on what view you are looking. When you faster, say offload, optimization feeds on GPU because you are not doing this CPU communication. This is widely used. This is actually most fine tuning has been done in the academic has been done with the LoRa, and the LoRa in many cases is enough. In some cases, you do see a loss. People do compare this one with fine tuning. Usually, it actually has a loss. LoRa will not be as good as the full fine tuning, but it's good enough so that it's something which people use quite a bit. It can be handled with checkpointing and so on. Yeah, basically, yeah. So this is something. Yeah, that's what we want to say about this technique. But the key idea is you just using trainable parameter become small by using low rank adaptation, right? One thing about this one is talk about where to apply, right? Uh, First thing you will apply in the original LoRa paper, especially, they are looking at attention. Attention, we have a two matrix. Is query, projection matrix. We have value, projection matrix, right? These two are they always are about there. And you could also do the key matrix. You could also do the O matrix, depend on where. Or you freeze those. So, but essentially, key part is here. But also, these are attention. People use LoRa to do all that. Also, MLP. You could choose that, but many people also do MLP. Basically, do both, right? But there's choices. I think here is more important. Here is lesser so. And in the original paper, they are much focused on this guy. But nowadays, you can apply to all the projection matrix. If you remember the transformer, you can go through that. You have this field is the matrix for the attention, and MLP has two matrix of MLP, right? Those are usually you do not apply LoRa to the embedding layers or whatever. That's typically these are the ones you do. Yeah. Rank R is one of the parameters, which the larger rank means more capacity, but certainly you more memory. So usually you use small rank 4, 8, and so on, 16, right, and so on. Yeah. So this is a typical setting, which you actually does. Scale alpha depends. I mean, usually you set up by certain rules, but you can also tune that if you want. This one is a little bit affect how the learning, how fast you are learning of these are in terms of alternatively you can do adjust learning rate and so on. There are different ways to do that, but essentially, yeah, this is about yeah. I mean, you could do this, and then you could do that. Yeah. So basically, essentially, this is a pretty typical range when you do this a lot. So anyway, so LoRa is considered the one of the more important, especially from the modeling perspective. How do you do adapters? And this is one which is frequently used, commonly used for a lot of tasks. They have this one is for the original paper. This is just putting in a figure setting in their table 4 of the original paper, LoRa paper. And basically if you look at essentially they say, okay, what is the rank, right? How dependent? Their observation is an even small rank, which does pretty good results. These are just two of the data sets which they evaluated on, and they do a rank with from smaller rank to the larger rank, and they apply to different things, right? This one is just a Q only. And certainly Q only doesn't really good, right? So then you have to use a QV. This is what it shows, right? QV signal outperform Q only, right? Even at a small rank, it's that. But rank is not that sensitive. You can use relatively smaller rank based on this, but at least you should use both. Then you say add to the auto attention. What happens, right? This one is just a small gap, which means that's why it's said this is optional, but the QV has to be there. And you can also add MLP layers. But essentially, the other one is a minor improvement, but the QV is the ones which are the more important ones, just from this figure. Yeah. This is a little bit of support what we are talking about earlier. This is from the original paper. And in practice nowadays, you just using a smaller rank with all the layers, which is one way to do that. So this is about the sensitivity rank, but this one depends, right? Sometimes people do observe there are more of difference. So rank tuning is definitely one thing people try to do. Depend on your data, depend on your task, and so on. But essentially, small rank is sufficient. So this is some good news that's also support LoRa and why LoRa is actually being surviving is effective. Here is one thing which I also mentioned. In the training, we know that, right? You freeze W, you are training A and B only for the LoRa. And one thing about nice thing about the LoRa, which also use with quite a bit of work in the LLM or even in the diffusion model or other things, right? Essentially is when you do the adaptation, assuming you already have this model before, you can save adapter checkpoints only. So adapter is only much smaller model, right? And then once you have original checkpoint, you have an adapter checkpoint, you can get back your original matrix. In the inference time, if you merge these two, there's no further. Let's say that basically there's no further penalty, right? So essentially, you can merge these two, and then this one. So basically, the training you have a full training, and one nice thing about you only need to save a small matrix once you are done with this training, because you just need to look at adapter. This is useful because you can save different adapters about one base model, multiple adapters, and then they have fine-tuned for multiple tasks, and with a parameter efficient way. And then you can actually load these different LoRa's to say these are different modification of my base model, focus on different capabilities. And this one is very useful for a lot of fine-tuning tasks, especially if you have many different fine-tuning to do. Yeah, inference can support multiple variations with a shared base model. So therefore, you have multiple variants of your base model, which cost a very small storage footage, like here. So basically, this is essentially something which one keep in mind, which will be very useful. Once we know the LoRa, QLoRa is pretty simple. It's just simple idea. It's simple ideas all based on the observation. Recall we mentioned that quantization is useful for inference, right? It's not good for training. It's good for inference. But observe LoRa, which you already have W0 is freeze. It's for inference only, right? So QRL just say, okay, instead of using 32 or 16 bits for your, this is a LoRa, right? This is a LoRa for your 16-bit transformer base model, right? 16 bits and a small adapter. This one you are using using 4 bits model. Again, because this is for inference only, so it was it's not a problem. So basically, yeah. And that's only idea it is. And basically did the experiment to say, oh, it works well. It works very well. So then that basically, yeah, that's it. So the difference of LoRa and QLoRa is you make a base model small. And what's a good thing about that? Because this one you can make very small, right? So even for large models, you can make a low rank as long as it's a low rank enough. This is small. The adapter part, adapter is smaller, but then this one still can be large if for very large models. So if you have 4 bits, you can get a much larger model. So basically, what they are doing is the following. So they are fine-tuning quantized 4 bits model with a standard LoRa adapter. And these 4 bits are frozen. It's the inference only. So that's why it's okay. And the adapters are adapted. This one is FP60. right? So this is fine. Forward update is usually this guy, right? So this we know. Yeah, we cannot compute this in 4 bits, but this one is okay. And preserve performance similar to full 4 bits outputting. This is what they observe and they study in the paper. For example, you can train a 65-bit model on a smaller GPU, 45 GB, right? You couldn't even 1 byte, right? But if you say I have very small LoRa, and I reduce this by half bits, which is let's say 32, right? 32, then you can actually manage as long as your rank is small enough. You could do a single 48 GPU to have a very large model. So these are some contrast. If in the academic, if you want to tune very large models, sometimes you do, right? QLoRa would be the option to do that because you can fit a very large model in a relatively small GPU. So this is a good technique. Yeah. Either LoRa or combined with quantization becoming QLoRa will be pretty standard way to do that. To fine tune that. Yeah, this is about all we do. I think in the summary, so we just quickly get some summary about what exactly we have talked about, right? First, we talked about memory consumptions. The GPU memory is what matters in this resource efficient. If you think about all the techniques we went through, these techniques are all to do with saving GPU memory. And putting as much computation as the GPU will be matters. If not, you can move some of computation to CPU, right? But the GPU memory, what is the parameters? You have gradients, you have optimizations, you have activations. Actually, you also have attention, which is proportional to the context length, right? But this one is another thing which it also deal with. Mixed precision is a standard because it saves the parameter and the gradients, right? So this is what you know, and this is standard for the training. And this both come from memory efficiency. Also, calculation is faster because modern GPUs are optimized for this. Quantization mainly helps the inference, which further reduced to 8 bits or 4 bits. So that's actually some more than one play with 2 bits, but I don't see things to be very stable in the 2 bits. So 4 bits is more reasonable. You see that quite a bit. 8 bits, 4 bits in the inference, pretty standard. Zero offload is when you cannot store all your parameters into GPU, you can move optimizer states into the CPU. This one will train models which you cannot train before, but certainly they have trade-off. Mostly trade-off is not CPU is too slow, but it's because of the communication between the CPU and the GPU. So you do have, but then you can train something which you cannot train if you don't do that. Gradient checkpointing is more for the activation, right? Compute the activation to cut memory, and basically skip some computation of the activation in your forward, and then you refill this calculation in the backward. So you just need to know this, but of course this one is helpful when you have a larger batch size or larger sequence length, right? Flat attention, this is more specific for the transformer, for the attention calculation. Essentially, you try to help with a long sequence, long context length, right? So this include the long context length, and that's useful. This is slightly different than the others, but if you look at the flash attention, it's related to the gradient accumulation. You just different batches, you are putting that a smaller batch at the same time, right? Gradient accumulation is more about simulating larger batch from smaller batch. And the LoRa, if you think about that, it's just LoRa can make a trainable parameter smaller than previously possible. And then compare with the gradient checkpoint, compare with actually zero offload, you save all the parameters. You can put all the parameters in your GPU memory. Therefore, you can train faster than the zero offload because you save the communication. So, and this is pretty common. And the QLoRa is similar, except you just make this even smaller bits in your base model. You can train much larger model, Q model, right? So, yeah, basically this is a reference, and also we provide a notebook. They include everything of this, so you can play with that. And the play of this notebook requires a GPU. You can install the packages, and you can play with that, or you can just look at the output. Output enable everything simultaneously, but you can try to turn off everything yourself in the notebook. So that's all for today. Okay, thank you.